All right, let's go over exercise 8. This is from section 2.5. So talking about the chain rule. So we have these two functions, f and g. We're composing g inside of f, and we want to look at the derivative of that composite function. So this is, the kind of the quintessential use of chain rule. I want to take a derivative of a composite function. So what is the derivative of h going to look like? So when we take a derivative of a composite function, we take a derivative of the outer function, in this case f, evaluated at that inner function left intact, and then we kind of work from the outside in. So we've taken a derivative of the outer function. Now I want to take a derivative of the inner function with its input intact, but its input is generic x. So this is as far as we have to go. So this is what this is what this derivative is going to look like now. So this right here is true generally for any function h that's defined this way in terms of f and g. So now let's fill in some of the details for us. So let's actually write down what the derivative of f and g are. The derivative of x cubed is 3x squared. That's a power rule. What's the derivative of g? That's going to be cosine of x. So now I can start filling these details in. What is f prime of g of x? Well, f prime is 3x squared, but I'm not going to have, so f prime of x would be x squared, or sorry, f prime of x would be 3x squared. So what does that mean that f prime of g of x is? Well, g of x is g of x is sine of x. So f prime of sine of x is going to be 3 times sine of x squared, or the way we typically write that is 3 sine squared of x. So this is f prime of g of x, and then we want to multiply that by g prime of x, which is cosine x. So here's my derivative. So this right here is h prime of x, but I want to evaluate that at pi over 4, and I want to do that exactly, which means I'm not going to approximate anything using a calculator. So 3 times the sine of pi over 4 squared times the cosine of pi over 4. Pi over 4, that's a 45-degree angle. So what is the sine of pi over 4? That's going to be equal to 1 over radical 2. Cosine of pi over 4 is also equal to 1 over radical 2. So now we can start filling or evaluating this. So 3 times 1 over radical 2 squared times 1 over radical 2, or 3 times 1/2 times 1 over radical 2. So 3 over 2 radical 2. So this is the exact value of that derivative. Moving on to part B. Which function is changing most rapidly at 0.25? So h, the way we just defined it, or r. So if we're talking about the change of a function, then that information is going to come directly from the derivative. So I'm not going to bother differentiating h prime of x again. We just did that. So let's remind ourselves. 3 sine squared of x cosine squared of it, or sorry, cosine of x. Okay, right. But now we want to evaluate this, composing the same two functions, but in the opposite direction. So if r of x is equal to g of f of x, then what is that derivative? R prime of x is equal to the derivative of the outside function g, evaluated at the inside function f, times the derivative of the inside function f. And I'll just remind ourselves here, what is g prime of x? Just what we said it was. So our f and g functions, the base functions that we're composed together, these are the same, so I'm just going to write down their derivatives the way I did in part A. But now we're going to use those ingredients in a different way. So what is G prime? And that's cosine of x, except I want to evaluate that at, at f of x. So this will be cosine of x cubed times f prime, so times 3x squared. So that's equal to 3x squared times the cosine of x cubed. So now we have both derivatives. We have r prime of x and h prime of x, but we don't know which one's changing more rapidly at this base point. Let's go ahead and evaluate. I have h prime of 0.25. That'll be equal to 3 times the sine squared of 0.25 times the cosine of 0.25. So that's approximately equal to what? 0.25. All right, so I'm getting a value here of about 0.178. What about r prime of 0.25? So that'll be 3 times 0.25 squared times the cosine of 0.25 cubed. One thing I want to point out here is that there's a difference between, notice where I'm applying that power. In this case, I am first cubing 0.25 and then taking the cosine of whatever that value is. As opposed to, when we say things like sine squared of x, that means you take the sine of that value and then you square whatever that sine ratio is. All right, so back to this calculation. So here I am getting a value of 0.187. So very close, but I'm going to go ahead and say that the function r is changing more rapidly because r prime of 0.25 is greater than h prime of 0.25. Moving on to part C. Which of these functions has a derivative that is periodic? Okay, so we're being asked about derivatives we've already found. So let's write those down again. H prime of x is 3 sine squared of x cosine of x, and r prime of x, which is equal to 3x squared cosine of x cubed. So we're asking which one of these is periodic. Let's remind ourselves what a periodic function is. A function is periodic if basically it has if its behavior is if it repeats every on regular intervals. So sine and cosine are good examples because a sine wave looks like this. Starts at 0, goes high, back to the center, low, back to the center. A sine wave does this over and over and over again. And the difference between like what you just erased. Never mind. The difference between those basically the change in x that it takes for this graph to complete one cycle of its behavior, that's a constant value. So if I let x change by that much, I'll just get one more cycle of this graph. Sine and cosine are both periodic, but that's assuming that the way x changes is, it's not altered in any way. And what I mean by that is I can hopefully show you a compare and contrast to kind of convince you. In my top function here, I have sine squared of x times cosine of x. So basically what I'm doing here, I'm taking the sine of x, squaring that, multiplying that by the cosine of x. So I have a periodic function times a periodic function. That's going to be periodic. as x changes by 2 pi, it'll just repeat whatever the behavior of this function does. That's not going to be true of cosine of x cubed, because as x gets bigger, not only is x growing, but I'm also cubing that. So basically, the argument to this cosine, like the input to this cosine, is going to be increasing, as opposed to these where, x is just going to grow at a constant rate. So it's not going to be like altering these waves. So those reasons. And if you even want a clearer picture, I advise graphing these derivatives. Graphing these derivatives will also show that one of these is going to be periodic and repeatable. The other one's not going to be.